So far we learnt about discrete random variables. So now we are going to understand about continuous random variables. So what we are going to do this week, the learning objectives for this week is to understand. First, we define what is a continuous random variable and how it is different from a discrete random variable. We will introduce what is called the probability distribution function of a continuous random variable. We will also introduce the concepts of the cumulative distribution function and expectation and variance. We have defined all of this earlier for a discrete random variable, but now we are going to revisit those concepts and see how things change when you have a continuous random variable. We are going to look at the uniform distribution and an exponential distribution as examples of continuous random variables, and finally we are going to spend time to understand about the normal distribution and its properties. This is what we are going to do over the next 2 weeks. First thing is we are going to understand what is a probability density function. Before understanding and discussing and defining what is a probability density function, let's recall what we defined when we introduced random variables. We said that there are 2 types of random variables. I defined a discrete random variable as a random variable which took countable number of possible values. Recall when we had a binomial random variable, it would take finite values, but I could also have something like a Poisson random variables which takes countable but infinitely many values. The key thing to note is I can have a countable number of values. So whenever I am modeling counts, I look at discrete random variables. The more popular or the most popular of them are binomial, Poisson, hypergeometric, geometric, and we also looked at a discrete uniform random variable. So basically when you are looking at discrete random variables, you are counting something. But sometimes I do not have a count, I might want to measure. For example, I will have values taken on an interval rather than at discrete points. In such a case, when the outcomes are numerical but cannot be counted. In other words, if I am not able to count it, I am talking about a measure. So hence I am bringing in a concept of measure or a measurable set. Now the mathematics behind this you will learn in other courses, but what I want you to see is when I cannot count it but I have a measure or over an interval, we have a continuous random variable. So in other words, I can distinguish a discrete random variable which has positive values along a discrete points and I can count those points, whereas a continuous random variable is one that takes possible values that form an interval. That is, if I have a real line, it can take any value on the interval. Can it take negative values? Yes, it can take any value in this interval. I am not restricting it to discrete points. In other words, it can assume any value over an interval or intervals. This is the clearest definition. So I do not have a model for counts here, but instead of counting, I am measuring. So the minute I am going to measure over an interval. Again, recall when I had a discrete random variable, I said x takes the values x1, x2, xn, or if it is countably infinite, x1, x2 with probability x equal to x1, probability x equal to x2 and probability x equal to xn. We refer to this as the probability mass function. But in the case of a continuous random variable, x does not take the values x1, x2, xn, rather x belongs to a interval, and the probability mass function is in a sense approximated by what we call a probability distribution curve, and this is referred to as a probability density function. So, I refer to the probability density function by lowercase f of x. Let us define the probability density function in a more concrete way. So, let us consider any 2 points A and B. A and B are anywhere on the real line. It could be negative, it could be positive, they are just any 2 points. So, I have A is less than B, that is the only condition I have. The chance that x assumes, so I know that x belongs to the interval A and B, and the chance that x belongs to any such interval is dependent on the curve you are defining here. This is what I refer to as the probability density function, and the way I am defining it is probability x belongs to A to B is same as x lies between A and B, which is defined as integral A to B f of x dx. From our calculus classes, we know that integral A to B f of x dx nothing but the area under the curve enclosed between A and B. A crude way to understand this, or a intuitive way to understand this, is to imagine that I have a random variable which takes values really between A and B with a particular probability mass function. If they are taking infinitesimally close to each other, then I know that the chance of these, the probability of x taking each of these values is going to be the sum of these probabilities, which is approximated. In a sense, you know that the infinitesimal sum can be approximated by the area. Hence, the probability that x lies in an interval is the area under the curve, which is given by the integral. So, this f is what I refer to as a probability density function, or I represent it by the lower case f and x. Again, recall when we looked at the probability mass function, I said that the summation of all probabilities of x is equal to 1, and we said probability x equal to xi is greater or equal to 0 and is less than or equal to 1. These are the two properties I used to verify whether something was a probability mass function. So, the first thing I need to, the analogous is probability x equal to xi lies between 0 and 1. I know here I do not have a probability x equal to xi, I have defined a probability x is between an interval 0 to b, and I know that that is the shaded area that would lie between 0 and 1. That is the analogous thing which I need to understand. Now, the next thing, that summation of x belonging to xi, x belongs to 1, if my PDF is defined between an interval, now the area under the entire interval, so the area under the entire curve is equal to 1. So, over the range of definition of my PDF, my integral, the area under the entire curve is equal to 1. This is similar to the property that over all values of x, probability capital X takes the value xi is equal to 1. Of course, I needed probability to be greater or equal to 0. So, that chance that the probability density curve will never go below the x-axis, because it is a probability, it would always be greater or equal to 0. Now, there is a very important property which says that when I am looking at a continuous random variable, x belongs to A to B, and I am telling the probability of this is same as probability A is less than or equal to x is less than or equal to B, and this is regardless of whether the end points are included. In other words, when I am talking about a continuous random variable, the chance that the continuous random variable takes a particular value is 0, it takes a value in an interval. What do we mean by that? Probability A is less than x is less than A is integral A to A f of x dx, which is going to be equal to 0. So, the chance that x lies less than or equal to B and it is greater or equal to A is the same as A is less than x is less than B. In other words, the probability x belongs to a closed interval is the same as it belongs to an open interval. This is true only for a continuous random variable. Now, let us look at an example to understand what we have discussed so far. So, I have a figure and the examples and the exercises or certain examples we have been discussing so far are most of them, and some of them are from the textbook which has been prescribed, an introductory statistics textbooks by Sheldon Ross. So, even this problem is a problem taken from that textbook. Suppose I am given a figure with the probability density function that represents the time in minutes it takes to service a television. So, what does this represent? So, let us understand what it takes. On the x-axis, I have the time in minutes. The chance that it would take between 0 to 10 minutes, any minute, it is going to be 0.14. The chance it is between 10 to 20 minutes is going to be 0.15. So, here you remember that I am not asking what is the chance it would take exactly 10 minutes, I do not define that, but I can say 0 to 10 minutes is 0.14, 10 to 20 minutes is 0.15, 20 to 30 minutes is 0.14, 30 to 40 minutes is 0.13, 40 to 50 minutes is 0.11, this is 0.09, this is 0.01, entire thing should take 1. So, I would leave it as an exercise to compute what is the area here. The hint is integral of this entire curve is equal to 0 to 10 f of x dx plus integral 10 to 20 x dx plus 20 to 30 f of x dx plus 30 to 40 f of x dx plus 40 to 50 f of x dx plus 50 to 60 f of x dx plus 70 to, I do not know what is this, let it be b, 70 to b f of x dx. So, this is 0 to b f of x dx is the entire range, and I know that because it is a PDF, this should be equal to 1. Now, f of x dx or f of x between 0 to 1 is 0.14. So, I can check what is the area under this curve is given to be 0.14 because the areas under this curve. So, the area under this curve is 0.14. So, let me use another color. What is given to me is the area under this curve is 0.14. The area, this area is given to be 0.15. This area is 0.14 again, this is 0.13, this is 0.11. So, what we can check here is for this, so in this problem what I can see is 1 is equal equal to, so I can check that, which gives me this area is, this question mark is 0.17. So, the question we are asking here is the following: what is the probability the repairer takes less than 20 minutes? So, x is the time that is taken. So, the question I am asking is probability x is less than or equal to 20, and I know that is going to be the total of the area here, which is going to be 0.14 plus 0.15, which is going to be 0.29. The probability of the repairer taking less than 20 minutes is 0.29. What is the chance it is less than 40, and that area is going to be this area, and that I can again see is 0.14 plus 0.15 plus 0.14 plus 0.13, which is going to be 0.56. So, that area is 0.56. What is the chance that it is going to be greater than 50? Now, greater than 50 I know is going to be, there are two ways I can find greater than 50. One is probability x is less than, or remember this was 0.17 is 50, because this is the chance that it is less than 50, and this is going to be 1 minus probability it is less than 50, that would give me this probability. So, the orange shaded region, is what I have to find out, that is probability x is greater or equal to 50, and I know the orange shaded region is nothing but one probability x is less than or equal to 50, which is 1 minus 0.67, which is going to be 0.33. The other way I can find out is probability x is greater or equal to 50 is going to be 0.09 plus 0.07 plus 0.18, which is going to be 0.33. Sorry, 0.17, which is going to be 0.16 plus 0.17, which is 0.33. Both are going to be the same. So, the chance that the repairer will take more than 50 minutes is about 0.33. The next question we are interested in answering is, what is the chance that the repairer will take between 40 and 70 minutes, and this I am going to write it as probability 40 is less than or equal to x is less than or equal to 70. I know this is going to be 40 to 70 f of x dx, the area, and that is the shaded area which I have here, and that shaded area is going to be 0.11 plus 0.09 plus 0.07, which is 0.27. So, the chance that the repairer will take between 40 and 70 minutes is 0.27. So, what we have learned so far is to understand what is a probability density function, and probability A is less than or x is less than or equal to B is the same as probability A is less than x is less than B, which is in A to B f of x dx, which is the area enclosed between A and B of the curve f of x. Now, what is the cumulative distribution function of a continuous random variable? We will just introduce the definitions, and then we will look at specific examples to compute the same. Recall the cumulative distribution function is what we defined as probability of x is less than or equal to some point x or a. I defined this as f of a, and this was defined for all the points on the real line. So, if I am looking at a continuous random variable x, and I know that this variable x is between some point say b to c, it is defined, and my a is here. So, I have this f of x which is not defined for any of the points less than b and greater than c. So, if I have a point a here, the area, so my cumulative distribution function is just going to be this. Now, if my a is here, it is going to be 1 because I have minus infinity to this point a, which would include probability x is less than or equal to this, and I know the shaded blue region is already 1. Here it is 0, here it is 0 the probability, but under this the entire area is equal to 1. So, in other words, the cumulative distribution function is minus infinity to that point f of x dx, where f of x is my probability density function. Again, since probability x takes a particular value is equal to 0, I know that probability x is less than a is the same as probability x is less than or equal to a. So, I have probability x is less than a is also minus infinity to a f of x dx, and that is something which we have seen here, that probability x is less than 10 minutes or x is less than or equal to 10 minutes is the same, which is 0.14. Similarly, if you recall the expectation of a discrete random variable where x takes the value x1, x2, so forth with probabilities p1, p2, p4 was xi into pi over all the values of I. Now, x does not take discrete value, but x belongs to a particular interval. So, the expectation of this x is over x into the probability. So, it would be x into f of x dx over the range I have defined. So, expected value of x is expectation of x into f of x. Similarly, variance of x is expectation of x minus expectation of x whole square. So, I know that can be written as expectation minus expectation of x whole square into f of x dx, because I know expectation of x is x f of x dx. I stop here with these definitions. When we meet in the next session, we are going to look at specific distribution functions. So, we have just introduced that the equivalent. So, in summary, in my discrete random variable, I had a probability mass function. In other words, x took the value x1, x2, xn. Countability was a key. Here x takes a value in an interval a to b. Here I am counting. Here x is measurable. I had the PMF, the probability mass function, which was probability x takes a particular value xi. Here I have a PDF, which is the probability density function, which I define as probability x belongs to a particular interval is a to b f of x dx. In the probability mass function, I had this was greater or equal to 0 and summation over all values is equal to 1. Similarly, I can have that the density function will never go below 0 and integral over the entire range is equal to 1. That is what we mean. And we define a cumulative distribution function here as summation over all xi, probability x is less than or equal to xi. Here I am going to define it as minus infinity to a f of x dx. The expected value in a discrete case was xi pi. Here it is going to be integral f of x dx. The variance was expectation of x minus expectation of x whole square. I am going to have the same thing here, but it would involve my density function. So, you can see that the key difference is countability here, and here it is measurability. So, when you are going into higher or advanced courses, you will be talking about these are measurable sets. In fact, you talk about what are Borel measurable sets. I am not going to focus on that now. So, what lies ahead is we will be looking at specific continuous distributions. In particular, we will look at the uniform distribution and certain conditions that can be modeled using uniform distributions. We look at another important distribution which is used a lot in queuing theory, which is called the exponential distribution. The exponential distribution is very important when you are trying to model service times or inter-arrival times. So, these are the two key continuous distributions we are going to discuss, and finally, we are going to spend time in understanding what is the normal distribution. A lot of conditions can be modeled using a normal distribution. So, that is something which we are going to look at. But first we will look at uniform and exponential distribution.